In today's video, I would like to introduce you a very nice problem that was suggested by viewer. So here is the following setup. So our goal, we are going to prove this statement, which is n to the 6 minus n to the 4th plus twice n cubed plus twice n squared is not a perfect square. Okay, for all n is strictly superior to number 1. If n equals 1, it will be a perfect square. Okay, that's why it gave us this condition. Okay, now let's go ahead and proceed with the solution. So we are going, as we know that most of the time we are providing the proof by the way of contradiction. We are going through this one because we are going to assume this one is a perfect square. Then from there we are going to build our proof to extract the contradiction. Okay, so by the way of contradiction, suppose this setup n to the 6 minus n to the 4th is going to be a perfect square, x squared, for all n is strictly superior than number 1. Okay, what does this mean? Which means n is going to be written as 2 plus k, where is k is super equal to 0. Okay, so n is a natural number. N is strictly superior than number 1 is the same as n is super equal to 2. Okay, so now what to do? Before we use this value, I'm going straight to factor out this one. So how to factor this one out? I see n to the 6 here, I see twice n cubed. I'm going to build a perfect square by using these two terms. Okay, so get n to the 6 is going to be written as n cubed plus number 1, all is raised to the number 2 as a power. If I'm going to distribute this one, is giving us n to the 6 plus twice n cubed plus number 1. We are going to subtract this minus number 1 because we don't have it. Then taking this term and this term with this minus 1, build a second perfect square. So let's do that by taking minus sine n to the 4th minus 2n squared. Okay, then take this minus 1, put it here, becomes plus 1, so everything equals x squared. So I'm simply going to build a perfect square here. So we get n cubed plus number 1 quaternion square minus this term, which is n square minus number 1, all is raised to number 2 as a power, which equals x squared. Okay, if you take a look up here, I'm going to factor out what's inside of this one. N cubed plus number 1, it will be n plus number 1 factor n square minus n plus number 1. Okay, so let's do that. So I get here n plus number 1, which is a perfect square. Okay, factor n square minus n plus number 1 also is a perfect square because it's shared number 2 as a power for both terms, minus next term, which is n square. This n square also is going to be written as n minus 1 square factor n plus number 1 square, because I factor out this one on the form of the product, which equals x square. Since we get n plus number 1 quaternion square in each term, so I'm going to take it as a common factor here. Now let's take n plus number 1 quaternion square factor n square minus n plus number 1 square minus n minus number 1 square, which equals x square. Okay, since n plus number 1 is not equal to 0, I'm going to divide both sides by n plus number 1 quaternion square. So I get here this x becomes n x over n plus number 1, all is raised to number 2 as a power. Then cancel out this one, then factor out this one on the form of the product. I get n square minus n plus number 1 minus n plus number 1 factor n square minus n plus number 1 plus n minus number 1, which equals x all over n plus number 1 quaternion square, like this. I'm going to cancel out a lot of things here. This one it will be cancelled out with this one will be cancelled out with this one. I will be left with n squared is multiplied by these things. I get here the following. I get n squared minus 2 times n plus number 1 plus number 1 factor n squared, which equals x over n plus number 1 quantity square. Also, I'm going to take this n squared and divide it by both sides. Let's do that. So I get here this one factor n, all is raised to number 2 as a power. This one is going to be cancelled out as well. Also, if we take a look up here, this is a perfect square. Let's write it here. So this one equals n minus 1 quantity square plus number 1. Okay, I get this nice expression. Since the right hand side of this equation is an integer, which means the left hand side of this equation must be integer as well. Okay, so this fraction is an integer, is a natural number. Okay, let's replace it with a capital B, this fraction. Okay, then also, since I get a perfect square on both sides here, I'm going to move over this term to the left and make a difference of the squares and factor out that on the form of the product. So I get the following. I get b, this one is a b square because I'm replacing this fraction with b. Then I will have b minus this term, which is n, b minus n minus 1 factor capital B plus n minus 1, which equals number 1. Okay, now I have extracted a nice factorization here. What to do, I'm going to take this expression at the top and continue solving our equation. We have been working on this equation and coming up with this nice product. So with b is a natural number. Also, we didn't use this condition yet. Now I'm going to take this value of n and insert it back into here because we are seeking for the contradiction. Okay, now let's do that. I'm going to replace n with its value. So I get capital B minus 2 minus k plus number 1 factor capital B plus 2 plus k minus number 1, which equals 1. Now let's simplify this one more. So I get capital B minus k minus 1 factor capital B plus k plus number 1, which equals 1. So now I have a new expression here. I'm going to solve this equation by putting the equation system here. Since we get number 1, so I will have here b capital B minus k minus number 1 equals 1. Also, I get capital B plus k plus number 1 equals 1. Okay, now we are going to simplify number 1 from both sides. I will be left with capital B equals minus k. Then take this value of b and insert it back here. So I get here minus k, which equals 1. Then moving over this minus 1 to the right becomes plus 1, which equals 2. So I get minus 2k equals 2. Thus, k equals minus 1. This one, it's a contradiction. It's impossible because we have contradicted this assumption. Because k equals minus number 1, it's impossible because k must be super equal to 0. Okay, thank you for watching. I will see you next video. Bye.